All right, solving Newton's law problems. We've been developing this toolbox over the course of several of these videos and in class of tools we need to actually be able to solve Newton's laws problems. So this presentation is mostly review, well, it's some review and then a lot of examples of pulling the parts together. When I'm done with this video of just kind of explaining the ideas, I will work 3 more examples and they'll be in separate videos that you can also watch. The first tool that we have in our toolbox is trigonometry. Okay, we did the worksheet in class. We talked about sine, cosine, tangent. You can find the trigonometry video if you need to review that. It's using the SOHCAHTOA memory device to kind of help, but that's the first tool that we have in our toolbox. The second tool is Newton's law of motion, okay, which tells us that net force times time equals mass times the change of velocity. This net force means all of the forces added together. So the effective force, or the net force acting in a particular situation, has to do with how hard the object is being pulled in various directions. So here, for example, the example we've shown earlier, we've got this cart being pulled by 100 Newton force to the right, and let's suppose for a moment that there's 25 Newtons of frictional force. These two forces being in opposition to each other would reduce the effective amount of the 100 newtons, or the net force, would reduce it down to only 75 newtons. I would just subtract those two numbers. Or if there were 50 newtons of friction, or if there were 65 newtons of friction, I would continue to subtract 50 newtons effective force, 35 newtons of effective force. Okay? In all those cases, because when I do the canceling out or the subtracting, there's something left over, there's some non-zero value for the effective force, or the net force, we say that the forces are not balanced, they're unbalanced. In the case where the frictional force would be exactly equal to 100 newtons, then the forces would be balanced. I've got 100 newtons pulling to the left, I've got 100 newtons pulling to the right. Those two things would cancel each other out, and so we say that the forces are balanced in those cases. Unbalanced forces always mean that we have acceleration. Okay, we're going to talk more about that in Unit 5. Balanced forces, which is where we're going to spend all of our time for Unit 4, balanced forces mean no acceleration. No acceleration means that the change in velocity is 0. Up here in the equation, delta V would be equal to 0. So there's 2 examples, or 2 situations where we have delta V equals 0. The first is when the object is not moving. It's just sitting there. It's not going anywhere. It's not going to start moving. We call that static equilibrium. Static meaning motionless, equilibrium meaning balanced forces, so balanced non-motion forces. The other is dynamic equilibrium, meaning it's moving, but it's moving at constant velocity. So dynamic means motion, equilibrium means balanced, so constant velocity. Because the velocity is not changing, delta V equals 0, which means that the net force also equals 0. So in all the problems we're going to work in Unit 4, the net force will always be equal to 0, because the object will never be accelerating. It will be moving perhaps, but never changing, never accelerating. All right, the fourth thing that we have, the first tool we have in our toolbox are all the conversion factors between weight and mass. Okay, and just in class, we talked about those. 1 newton is 100 grams, 10 newtons is 1 kilogram, 1,000 grams is a kilogram. So we have those conversion factors that we talked about in class. And the fifth tool we have in our toolbox are force diagrams. We need to draw force diagrams. So here is an example. This example is like problem number 1 in your homework, 4.3. We have a brick or some object, a book maybe, I don't know what it is, sitting on a tabletop or on the ground. It's on a flat surface. The force diagram looks like the normal force pushing up and the gravity force pushing down. The mass of the object is 5 kilograms, which automatically tells us we know the force of gravity is 50 newtons. Okay, that ought to just be super fast, automatic for you. The equation that we write is we know that net force equals 0. So we have, where did I put it? Here it is, the equation down here on this corner. Okay, that net force equals 0. So I write that. Net force equals 0. Now, net force specifically means to total all the forces together. So this plus that. Fn plus Fg. has got to equal 0. I know that Fg is equal to 50. I see that it's pointing downward, so when I put it into the equation, I make it negative. Fn plus a negative 50 newtons equals 0. Therefore, the normal force must be equal to 50 newtons. Typically, when solving these questions, you're going to be asked, the question would have said, a 5-kilogram brick rests on the ground. What is the weight of the brick and what is the normal force? And so we found both of those things.